what do we mean by nanomaterials? So if we can consider the size, then size should be less than 100 nanometer, at least in one dimension. If we consider any material, if size should be less than 100 nanometer, at least in one dimension, then you can say that is a nanomaterial. But what is the importance of nanomaterials? Since these nanomaterials have high surface to volume ratio or quantum confinement effect, we can use those nanomaterials for several applications. If first I consider the gas sensing application, for particular a gas sensing application, generally selectivity and sensitivity, both things plays important role. Does nanomaterials have higher selectivity compared to the micro or millimeter materials? If that question comes in our mind, the first I'll give a basic example which was related to us. From that understanding, we can get a knowledge that yes, nanomaterials have higher selectivity compared to micro or millimeter materials. You can see here in my first slide that I put here two babies. One baby of around 5 months, another baby or another child is around 5 years old child. So one is 5-month baby, another is 5 years old child. So in front of them, I put their family members. Then I told both of them, that 5 years old child and the 5-month baby, to select any one from their family members. So if we told to select anyone from their family members, particularly if we consider the 5 years old child, so what will happen to whom he will select? He may select to his mother. At the same time, since he knows everyone, like his mother, like his father, grandmother, sister, or so in his mind, maybe 70% selection will come towards his mother. At the same time, also another 30% will be towards to his father or brother or sister. So means selectivity, in terms of selectivity, we can understand the selectivity will be 70% for the particular, for the 5 years old child. But what will happen when we will tell that 5-month baby to select any of one from their family members? I'm sure he or she will only come towards to his or her mother. Means he will select or she will select only to his or her mother. Means the selectivity in this case, particularly in this case, will be 100% towards his or her mother. So now if you can consider the size of between them, obviously the 5-month baby has smaller size. So from this basic example, we can understand that if we can reduce the size of a material, then the selectivity will increases, which plays an important role for particularly for gas sensing applications. And another way, breath from the literature we found, the breath is an indication of human health condition. In our breath, we are always releasing several gases like acetone, ammonia, ethanol, hydrogen, carbon dioxide, or carbon monoxide. And we found from the literature, if someone can detect a very particular amount from our breath, then you can say what the patient is. Like if in our breath from certain percentage, higher amount of acetone is detected, then you can say that patient is a diabetic patient. If in our breath, like ammonia will be detected, then you can say from the certain percentage, if higher will be detected, then you can say that is a renal disease person. If nitric oxide will be detected, then you can say that is a asthma patient. If hydrogen will be detected, then you can say that is a lung cancer. But to detect those amount, you can know that for a diabetic patient, if we go to the medical, then he has to do several tests. So means the cost becomes very high because they have to do like some gas chromatograph. So there are several techniques are there which are expensive, most expensive, and also several ways they have to do, perform. So still yet, there are on the other way, like those are the volatile organic compounds which can be detected by using gas sensors like metal oxide based gas sensors. But still yet, there are no such sensors, no such gas sensors are available in the market, like low cost gas sensors are available in the market which can detect trace amount of the several gases. So we think, why not we will prepare some low cost or cost effective materials which can detect those particular amount of those volatile organic compounds from our breath, or we can use as a breath analyzer. So generally from the literature we found that transition metal oxide plays an important role in these areas. Mainly tungsten oxide, tin oxide, those are very good materials is used as gas sensing application, used for gas sensing applications. To enhance the performance of those materials, they generally, people what they did, generally they use some noble metals like gold, platinum, palladium, silver. They decorate their materials on those transition metal oxides, on those like the tungsten oxide, the tin oxide, they decorated those or they engineered those materials by using some noble metals. Then their performance was increased. At the same time, cost of the device also increases. So it is important to prepare the material at low cost. So our first objective comes to prepare some hierarchical nanostructures which can detect the volatile organic compounds from our breath, and as we can use as breath analysis. We take here tungsten oxide, tin oxide, and we prepare this material in a simple way, only in a one pot synthesis methods. We prepare this material, and we found this material highly important to detect those several gases. Also, we reported for the first time these materials. How we prepare these materials, we generally take some precursor of those materials and we add it, and we use hydrothermal method to prepare this. Only tungsten oxide we prepared, only tin oxide we prepared. Then we just vary the tin precursors and we prepare the composite of tin oxide and tungsten oxide. So after this preparation of any material, when we prepare, then our aim is we have to characterize that material, what the material is. So to understand the structural property of a particular material, if we want to know that what the material is, the fingerprint of a material, to understand the structural properties, like to understand the phase of the material or to understand the crystal structure of the material, we have to perform X-ray diffraction. From powder X-ray diffraction, we can understand what is the phase of the material or what is the compound is. Then to understand the optical properties of the material like band gap or optical absorption, we have to do UV visible technique, where we can understand the optical properties of that material, of that particular material. To understand the size, shape of particular material, we have to do ACM or FEACM, like field emission scanning electron microscope, or we can also from transmission electron microscope, we can understand what the morphology or microstructure of a particular material, where we can calculate the size or shape of a material. Then to understand the surface area of a material, we have to do BET surface area. So that material we prepared, like tungsten oxide and tin oxide, what the material we prepared, we first check what the size of the material, what is the morphology of those nanostructures. You can see the first one, the first in the figure, if you see image in the first figure, that was only WO3, only tungsten oxide. But you can see that from that figure, we can understand those are flower-like shapes, flower-like hierarchical flowers. And those flowers consisting or composed with several nanoplates. You can see on that insert, that is the high magnified image, and where you can see those nanoplates are clear surface. Then we prepared only tin oxide, where in figure B, where we got only nanoparticles. And we found the size are around 5 to 10 nanometer. And when we prepared composite by varying this tin precursor during the synthesis of that composite, we take one material, we prepared one nanomaterial by very less amount of this tin precursor. Another material we prepared by moderate amount of that tin precursor. Another material we prepared with a high amount of tin precursor. And that also things, whatever we prepared, that was reflected also in our FES images. You can see from the figure C that in that you can see the high magnified, on that high magnified image, very tiny bright particles are decorated on that plane surface of the tungsten oxide nanoplates. And when we can see also these nanoparticle size are very small. When we little bit more amount of tin precursor we add during the preparation of this composite, you can see that moderate amount of like some little bit higher amount of these tin particles are decorated over the nanoplates. On that inside image, you can see that the concentration of tin particles, tin oxide particles also higher. And when we put some higher amount of these tin particles or higher amount of tin precursor, then you can see that agglomerated tin oxide particles are decorated on the plates. So there are things also reflected in our, like to understand in a material, when we prepare some materials, to understand the elemental composition, what are the elements present on that particular material, we have to do energy dispersive X-ray spectroscopy or ADS analysis. So from that ADS analysis, you can see that also that tin precursor, when we varied, then the element, the atomic weight percentage of tin also changes. You can see for higher amount of tin, you can see the higher amount of tin, because the higher amount of tin elements are there, tin atomic percentage are there. In moderate also, moderate amount of atomic percentage, atomic weight percentage are there. Similarly, only tungsten oxide, there is no peak of tin. Similarly, only tin oxide, there is no peak of tungsten. And particular this paper, recently already it was cited 150, so more than 100 citation already done with this in particular for this paper. So after this one, so whether to further character, to further understand about that morphology or the microstructure, we again did the TM analysis. From the TM analysis, we also found that only tungsten oxide, those are nanoplates. Only tin oxide, those are particles, size around 5 to 10 nanometers. And when we prepare some composite, you can see that on that plates, those particles are decorated. So from that TM analysis with the transmission electron microscope, we can understand that these are correlated with our FESM results. The difference between FESM and TM, that in FESM, that is a 3-dimensional image we will get, and in TM we got 2-dimensional images. So to understand whether this one is tungsten oxide, tin oxide, or only tungsten oxide or only tin oxide, to understand this as phase, to understand the crystal structure, we did X-ray diffraction. You can see from that XRD spectrum, from this XRD spectrum, we perform all the samples. We found from that the first one, only tungsten oxide, it was matches with the tungsten oxide. Only tin oxide, that sample we prepared, we got tin oxide. However, when we varies the tin precursor, we did not observe any extra peak in the tungsten oxide plates, any extra peaks for tin oxide. But on the other way, but the intensity, we can see the intensity was increases, which suggests that crystallinity increases when we incorporate the tin oxide, the tin precursor into that sample. But there is no, on the composite sample, we do not found any tin oxide peak. This is maybe attributed to that very less amount of, since we use very less amount of tin precursors, so we did not observe any peak. But to understand the chemical state or oxidation state of a sample, of any sample, we have to do X-ray photoelectron spectroscopy. From that, we can understand what is the chemical state of the material. or oxidation state of a material. Also, we can understand the chemical composition of a material. So from this XPS or X-ray photoelectron spectroscopy, we can see that on the surface spectra, you can understand that yes, both tin, tungsten and oxygen all are present. But from this oxygen peak, we can, and also from this tin peak, we can understand that this is SnO2, not Sn. So from that XPS analysis, we understand that this composite was tungsten oxide, tin oxide, not tungsten oxide, tin composite. So after we successfully prepare these nanomaterials, these nanostructure materials, then we use these nanostructure materials for gas sensing applications. And we found, particularly we found these materials are highly selective and also those are temperature dependent. We tested for all the 6 samples we tested for ethanol, for ammonia, for ethanol, for acetone. These are primary biomarkers. We found particularly one sample when we uses some high amount of tin precursors, that is, this was highly selected and this was highly sensing towards ammonia at a temperature 200 degrees centigrade. And when we use a moderate amount of tin precursor, we found at 300 degrees centigrade, it was highly selective towards ethanol. And we found for only tin oxide, it was highly selected for acetone. And also to understand the selectivity, sensitivity, we also tested several other gases, whether this was only particularly selective for this one or for other gases also. You can see that from the selectivity also we found the high amount of tungsten oxide was highly selected for ammonia, and the moderate amount of tin precursor was high, that composite was highly selected for ethanol, and only tin oxide highly selected for acetone. Now, if we can tell that this shows the high concentration of tin oxide precursor, tin precursor shows towards ammonia and this one towards ethanol and acetone. If without science we can present, then it will be not acceptable. So to publish a good paper, the important is that what is the science behind it, we have to find out. Why particularly high amount of, when we use high amount of tin precursor, it was highly selected towards ammonia. By moderate amount of tin precursor is highly selected towards ethanol. By only tin oxide is highly selected towards acetone. So generally when we prepare some heterojunctions, like we take tungsten oxide and we take tin oxide, means there is a heterojunctions between tungsten oxide and there is a depletion region also between the tin oxide and tungsten oxide. So more number of tin oxides should be there, then more number of junctions will be there, more number of active sites will be there. So what will happen? We found that kinetic diameter of those molecules like ammonia, ethanol, and acetone. We found the kinetic diameter of ammonia molecule is the smallest one, that is 0.26 nanometer. However, for ethanol that is 0.45 nanometer, for acetone that is 0.47 nanometer. So since the kinetic diameter of this particular ammonia molecule is very small, and particularly here when we have taken a high amount of tin precursors, means more number of junctions will be there. Also from this FESM image, we found that agglomerated tin oxide particles decorated on the plates. So since more number of junctions will be there, more number of active sites will be there. So there is a chances that since the ammonia molecule is smaller in size, so it can interact with each junction, so that we can able to get high selectivity for ammonia, for particularly for high amount when high amount of tin precursors are there. But in case of ethanol, since that ethanol, the kinetic diameter of ethanol is 0.45, little bit larger, so it cannot interact all the junctions for high amount when high amount of the tin oxide particles will be there, or in agglomerated case. So we cannot get high efficiency or high selectivity for the highest amount of the tin oxide particles. But in case of moderate amount, it is able to interact with all the junctions, so we will get higher amount of the selectivity for ethanol 1 at moderate concentration of tin precursor on that W3 tin oxide composite. And for tin oxide case, we found that particle size plays important role. Since the particle size of this tin oxide are very small, like 5 to 10 nanometer, so means according to the rule, we know that in general, we know that if the Debye length, if it will be twice of the Debye length, like the tin oxide particle, the length is 5. So if it will be twice, then it can interact the maximum number of oxygen molecules from the air atmosphere. That's why for tin oxide case, we will get high amount of selectivity for acetone at higher temperature. So from this, we understand that that material we prepared in a single process, and we do not use any noble metal free. We prepare these nanostructures materials, and we found those materials are highly selective towards several gases or biomarkers, towards acetone, ethanol, and ammonia. And we calculated also LOD and all those things, and we found that we can use also this one for breath analysis. And particularly this material also, we also given a table on that particular paper also we mentioned, and we found that our result was higher 10 times, 20 times higher compared to the, not only the pristine one, but also compared with noble metal oxide or noble metal composites. So here we can understand that the performance of the towards ethanol or towards ammonia, it was the composite shows higher performance compared to the pristine or pure W3 or pure SNO2. So here we engineer the nanostructures of tungsten oxide and tin oxide. We engineer those two towards to prepare a hybrid or heterostructures which shows higher performance towards the gas sensing applications. So now also we engineered also nanostructures for other applications, the same one, but we prepared with some platinum, and we found those are very good materials for fuel cell applications.